Now this is stream functions. This is going to get a little bit more heavy, but it's going to make a lot of things clear of what a lot of these equations are supposed to represent. But anyway, we'll start with the continuity equation here. The derivatives of u1 with respect to x and u2 with respect to y are partial derivatives, which equals 0. It's continuity, meaning basically that everything must go somewhere, I think. Well, anyway, u equals u1 of I plus u2j, which are our unit vector components i's of j. So these are Cartesian coordinates. If we introduce a scalar field, our psi x of y, such that u1 equals this function over y and u2 equals the negative of this function over x, then for any function our continuity automatically the continuity is automatically satisfied as such here. Now by the theorem of mixed derivatives, our second derivative of y with respect to x and y equals our second derivative of x with respect to y and x, which subtracting one from the other equals 0. This is the mixed derivative theorem. Now here's an example. We find this stream function for a uniform flow with a velocity field of u of uppercase U cosine alpha I plus U sine alpha j, where we're dealing with polar coordinates this time around. Now U and alpha are constants for the uniform flow. U1 equals our derivative of the function with respect to y, which equals U cos alpha, and likewise for U2 here we get U sine alpha. Now we integrate second equation, we get this, and this is our arbitrary function of integration, because with partial derivatives we get this back rather than a generic constant. So we have a function of integration, because we're dealing with more than one variable when it comes to partial derivatives. We're always holding one constant and so on. But now our derivative of our psi with respect to y equals 0 plus the derivative of our function of y, which equals u cosine alpha. Now the first equation integrating, we get f prime y equals u of cosine y, which we determined here. Now this gives f of y equals uy cosine alpha plus a. A is a constant, hence a streamline function is given here. The lines psi constant are defined by this equation, which is a constant, we'll say equals to b. Now we write b minus I over u cosine alpha equals c, and also y minus x tan of alpha equals c, which we will obtain this. Now let's just move on to another equation. Example. This is vorticity. So this is fluid moving around something, usually cylinders of some kind, which are the go-to things, I think, in many fluid dynamics lectures or books or courses or whatever. But vorticity, we get a stream function given here. Our psi equals u of r sine theta minus u of a squared sine theta over r. Now in polar coordinates, u equals u of r er plus u of theta e theta, where u of r equals this from the stream functions first given. So u of r equals u minus ua squared of r squared cosine theta, and likewise for our theta component here. Then our path integral around c of u dr becomes this, which we already obtained here. So this is an integral over udr. Now from negative pi to pi, u of theta of rd theta, since delta r equals r delta theta e of theta, we get this, because this is our like these are generally volume or area kind of components which go into the integral. And when we're dealing with, like, say if we're dealing with spherical coordinates, we get r squared sine squared theta, I think, and then our other components, well, dr, d theta, d theta, and so on. But anyway, which we end up with this once we're plugging in, and we can pull all these out because these are constants, and that's what we do with integrating when we're not integrating with respect to that, and it's a constant. We can just pull it straight out from the other side of the integral. So now we're only integrating over sine of theta d theta, which equals 0, and that's the case of a vorticity around a cylinder. Now a line vortex is this: psi equals kappa over 2 pi ln r plus some constant. So if we choose constant to equal this, then for psi equals 0 when r equals a, we will get this as our function. Now streamlines of flow around this cylinder here. Of the top part is pi over 2, the bottom part is minus pi over 2, and this is our kappa here, which is a negative, operating in a negative direction, and this is the a is a radius of our fictitious sphere, and a point 0, and this is fast flow going further away from the cylinder, and this would be our equation in this instance for our stream function. Now let's move on to Kelvin's theorem. Now assumption 1, fluid is inviscous, so Euler's equation can be used. Assumption 2, the fluid is incompressible, so our pressure equals our density equals our initial density, which is constant. Assumption 3, the vector field F describing a body force per unit mass is conservative, so F can be written as this, where this omega is a scalar field. Now the circulation around any closed curve C moving with the fluid remains constant in time, thus our kappa equals our path integral of u dr. Then our d kappa of dt equals 0. Here, in general, u may be a function of both time and position. Now, moving on. Now, here's Reynolds number. Now, we assume that the speed of a fluid a long distance away from a cylinder is u, and that the radius of a cylinder, a, the density, rho, and viscosity, mu, and this gives rise to an important quantity associated with the flow, which is this, the Reynolds number. Now if the Reynolds number is much less than 1, the flow is steady. If the Reynolds number is greater than 1 and 30 is greater than the Reynolds number, the flow consists of 2 regions, in front of the cylinder and some distance behind it. Now this is an example for the Reynolds number of equals 10, and we end up with these vortices behind the cylinder as the flow passes the cylinder. Now for 40 is Reynolds number is greater than 40, and 4000 is greater than Reynolds number. When the Reynolds number reaches about 40, the character of motion changes abruptly. One of the vortices behind may break away from the cylinder and travel downstream, but then the fluid quite quickly replaces this broken off vortex by another one, and so on and so on. And this is with a Reynolds number of 100. Now this is a Reynolds number of 10 to the 6, which would have real world drag and separation. This kind of flow is more reminiscent of a jet engine, by the looks of it. This is incredibly high Reynolds number, so we would get this kind of turbulent, chaotic kind of flow. And And that's our stream function for fluid dynamics. Please do like and subscribe.